Hello, welcome to video 12 in radioactivity, transmutations and chain reactions. What do we mean by that? Well, transmutations are when you're changing a nucleus by interacting with particles, and there's a number of ways of doing it. You've probably already done a couple of questions where we've bombarded nucleuses with neutrons or beta radiation, no, alpha radiation would be more likely, or protons, things like that. And it's where you get a change in the nucleus. And so let's do a couple of examples and you'll get the general idea. So there's ways of doing it: alpha bombardment, neutron bombardment. Basically we're sending very fast alpha or neutron particles, aiming them at lots of nucleuses, and they're going to hit some. And so here's an example. We take a alpha particle and we fire at beryllium, and we get carbon-12 given off and a neutron. Now how would you write that as a nuclear equation? Well, remembering that in terms of, let's get a better colour, in terms of our equation we always have an arrow, and this would be the before and this is the after, and this works in chemistry as well. And so what are the before particles in this equation and what are the after particles, sorry. And we could say, well, this is a before, so it's got to go there. This was here because it's got to be there to be hit, so that's got to go there. And then if these guys are the before, the carbon and the neutron are the after. And if we put that into an equation, should appear shortly, we get this. And again, with our nuclear equation, everything should balance. The top should balance on the left and the right, and the bottom should balance on the left and the right. Let's get rid of that drawing. So that wasn't too bad an example. And so that would be an example of alpha bombardment. Now, nuclear fission. We can take fission means pry apart or break or shatter, and so in nuclear fission we're talking about having a very large nucleus break into smaller nucleuses. And typically we would be talking about uranium and plutonium, and typically we'd be talking about the things that are happening in nuclear reactors or nuclear bombs. That's the sort of scenarios that you have. So when a heavy nucleus splits to form two lighter nucleuses, roughly the same mass, but not exactly the same mass, and that's where the energy comes from. Mass gets converted to energy using the equation E equals mc squared. So all that energy you see in a nuclear bomb is from mass being converted to pure energy. And you usually get some neutrons given off as well as part of the reaction, because of the whole neutron stability happening. So, and mostly it's the result of neutron bombardment that starts it all off, but not necessarily. But you can force it to happen. And so here we have a big heavy uranium nucleus. We fire in a neutron, which we can do. It splits into strontium-90 and xenon-142 and gives you 3 neutrons. Now those 3 neutrons are the interesting part in all this, because they can then go on and hit another heavy uranium nucleus, and this process can happen again and again. And each time this happens, this whole reaction here happens, energy is released. And these neutrons can then result in what's called a chain reaction. If more than one of them hits a heavy uranium nucleus, you're then getting a growth in the number of fissions that's occurring. And that growth gets faster and faster, because if let's just take the best case scenario, if all 3 of these hit another nucleus and caused another fission, you go from 1 fission to 3 fissions to 9 fissions to something else. and it rapidly gets into massive numbers, because this is almost instantaneous, within fractions and fractions of a second. And this is a chain reaction. And this is an example. In this case, they're just doing 2 of the 3 neutrons are absorbed, and so you have your first generation happening. They produce new neutrons, but one of them's lost. One doesn't actually interact with the nucleus. It just whizzes off and either gets absorbed or interacts with other stuff around, or just travels all the way through without hitting something. Then you get 2 fissions happening, and then you get 4 fissions happening, and so forth. And this is a chain reaction, because you're getting a bundle of energy there, you're getting twice as much energy there, you're getting 4 times as much energy there. Suddenly you get a massive amount of energy being released. Now there's a video on your OneNote that shows you just a modelling of a chain reaction, so how fast it can happen. Now that's fission. What about fusion? Well, fusion is when you take lighter elements and you join them together to make more stable, heavier elements. And that's what's happening in the Sun, and we can make it happen as well. In this case, we're bombarding nitrogen-14 with an alpha particle, and we're forming oxygen-17 and a proton. And because of the mass difference here, some energy may be released, but this is more a transmutation, where we're actually trying to manufacture isotopes, or this could occur in nature, and so we would actually be measuring oxygen-17. Here, this is the reaction we mentioned before in terms of what happens to nitrogen-14 in the upper atmosphere to form carbon-14, which is an unstable isotope of carbon. Now you should be able to write the equations for both of those, and they should balance, of course. So just some terminology. We've had nuclear fission, splitting a large unstable nucleus into 2 smaller ones and giving off neutrons and energy. We've had an uncontrolled chain reaction. That's where the neutrons released cause more fission reactions, and the reaction rate increases rapidly, and fission proceeds unabated. That's a word you don't hear very often. Now, what do we mean by critical mass? Sometimes you might hear the term critical mass used in relation to this. Well, this is the minimum mass of the fissionable material. So that would be the uranium-238 we were talking about before, but it could be any of the things that we're using in fission. And so the critical mass basically means you've got to have enough nucleuses to sustain the chain reaction, and it's got to be of a high enough density of those nucleuses. You can have a lot of uranium-238, but if it's not in pure form and there's all these other atoms around, you won't get a chain reaction. You've got to refine it, make it pure, and then make it fairly dense as well, to get rid of or to increase the likelihood of those neutrons hitting other nucleuses. And that's what happens when you refine uranium ore into fuel rods to be used in nuclear reactors, or when you refine uranium or plutonium to make a bomb. Now, an uncontrolled chain reaction is where all the neutrons are released and can possibly interact with the other nucleuses. What does that look like? Looks like this. Here you start off with your reaction, you get your products given off, 2 neutrons go off, make off other ones, and you get more and more neutrons, more and more fission happening. A controlled reaction is what we do in nuclear reactors, and same starting point, but what happens is only a small number of the neutrons get to go off and cause more fission. We actually put in something that absorbs neutrons. So here, this neutron is absorbed by this material. Now, the most common material used to absorb these neutrons is something like graphite. But there's a whole variety of other substances. They should have actually made these different colors, because you can see that here two of the 3 neutrons are actually absorbed, and one goes on to cause fusion. Fission. Now, what's the difference between a bomb and a controlled reaction? Well, it's the difference between a chain reaction and a controlled reaction, basically. And so there's our starting point. Now, this would become a bomb if these neutrons had the chance of hitting more target nucleuses. It becomes a chain reaction when the neutrons aren't free to go and interact with the other nucleuses and they get absorbed. And there's another example of two different. This is a bomb or an uncontrolled reaction, and this is a controlled reaction. And we do this in nuclear reactors, and that way they can control how much energy is being released by this fission, and therefore they can control how much energy is being converted into electricity. And so they use the control rods to control this reaction. Now, clearly, if it's not a controlled reaction, it blows up and releases a massive amount of energy. Now, on your OneNote, you've got the video of all the nuclear tests in that period, which is interesting to watch. And here's just the basic, very simplified diagrams of how an atomic weapon works. Basically, this is your fissionable material, uranium-235. The cone and the semisphere here are actually have to be together to form a critical mass. And the way they get them together is they use a detonating charge and they ram this this cone into this sphere shape, and that produces a critical mass, and bang, it goes off. Another variation is where they can use, and this is quite a complicated one, but the principle's the same in a number of different ones. What they have is they have uranium-238 as a sphere, but it's a hollow sphere, and it's not the critical mass. It's not dense enough to actually cause fission to occur. And so what they use is they use explosives, and the shock wave from this sphere of explosives causes the uranium-238 to collapse and initiate fission, an uncontrolled chain reaction, and that releases another shock wave in this case, and that shock wave causes a plutonium sphere to go critical, and that's how you get a plutonium bomb, or a H bomb, sometimes referred to. Much more powerful. Now, how do nuclear power plants work, or nuclear reactors work? Basically, their principles are fairly the same. They're very complicated machines. They've got to have innumerable fail-safe mechanisms because of what you're dealing with, but the basic design is fairly simple. That is, you have your core, and in the core you have your fuel rods, which contain your fissionable material, and then you have control rods which you raise and lower, and by raising you free up all those neutrons to hit more fissionable material, and so you raise the rods to actually get more energy out, and you put the rods in to shut it down or control it. It doesn't shut down the fuel rods, there's still fission occurring, but it's at a much less rate, and it can't go uncontrollable. And most of these use gravity's fail-safe systems, so everything else fails, the control rods just fall into place and shut down the reactor. Now, in between all the fuel rods, there's got to be a way of transferring the heat, and usually a fluid is put through, sometimes something like solid sodium metal, because it's such a hot, extreme environment. That hot metal or hot substance then goes into a heat exchanger, generates steam, steam goes into a turbine, generates electricity, the fuel is pumped back, the coolant is pumped back, and everything that's radioactive, which is the cooling fluid, the steam doesn't become very radioactive, so that's not really a worry, is within what's called a containment vessel, which is a specially constructed sealable concrete block, basically, that can be shut down at a minute's notice. Just a different design, simplified again, same basic principles: fuel rods, control rods, heavy water in this case, heavy water used as the coolant. And these are actual nuclear cores. Because they're kept underwater in some cases, you get this eerie glow. That's not a special lighting effect, it's actually caused of the radiation. It's caused by the particles being emitted travelling faster than the speed of light in this medium, and therefore they emit radiation, and it's characteristically a bluey colour. Now in the next video we're going to talk about nuclear accidents, because there have been a few, and so we just have to put them into context in terms of our radioactivity. So, cheerio.